Yeah. So if I go to, where did I do partial fractions? So here. So is where we did this. Okay. Okay. Now, like this, what I did is I pulled out the half. Yeah, it's here. I pulled out the half. Okay. And this is now what you get. Hmm. So now, are you saying my standard form is a bit sus? Is that what you're saying? So what was the sampling time? It was zero point 0.5. Okay. So now, in so doing, you get, we end up with this over here, right? Yeah. So perhaps I should do it in a different color so you can see. So this, did I negate this? I really hope I did, because if I didn't, that's the, no, but I believe I did. Okay, that's that guy. Okay, like, you let us know when your thing is okay.
Yeah, it's no longer freezing right now, but I'll just check if it doesn't act up when I share my screen again.
Okay. Yeah. Well, look, it's not technically, technically yes, but technically to get from here to here, you first inverse Laplace, then take Z. But because we know of the equivalence of this form to that form, we can just do that. So you see, I'm saying take, yeah. So technically yes. Let me just see what I did here. Oh, pizza. So this one is minus in front of Z squared. So yeah, that's fine. No, this is okay. This is okay. This is okay. So there's no mistake, yeah. There's no mistake, yeah. So if you plug in these values, do you get the same thing for your denominator? Please just check. Okay, I'll actually write it out for us together, so we can see what's going on. So for the first bit here, what I will say is Z into exp minus alpha with 1 multiplied by sine 0.5. Yes. Over z squared minus 2 multiplied by z multiplied by exp to the minus 1 multiplied by cos 0.5 plus exp. No, 0.5. Okay, here we go. Why are they leaving this as 1 over e? Why are they allergic to that? What's 1 over e? 0.7. Yeah. Okay. So that's 0.367. Okay, cool. So that was in fact correct. Now, how do you do it for the other one? Well, well, not partial fractions here. So I just wanted to calculate the value there and the value. So I'll call that term 1. And I'll say term 2 equals. I do not think there was a mistake here. It's just the nature of the cookie. Minus z squared minus 2 e cos. Yep. Yeah, but sometimes you need to help Wolfram out because if you ask it to compute something that's very long. Yep. Yep. Yeah, so that was a problem. I didn't put the brackets. See? So that's exact. So that's exact. So you say minus plus yeah, that's fine. Is it still simplifying or not? Is it? Yeah, wait. but I forgot the halves. There's halves on the outside of this. So there's a half. Right. No, but wait. But hang on. No, this is not what we got. Is it? For that intermediate term. Okay, hang on. I'm gonna say a half. And then this is plus z over z minus 1. Okay, where's the final simplified form? Is that not what I wrote down? Because then that looks very different to. Yep, that looks very different. Yeah. Yeah, okay. So, you know what? I'll resort to by hand then. But it does. I mean, this is what we had. This is what we had there, but then okay, so let's go back to where it's simplified. So alternate forms. This is it. That's the form. That's the form I wanted in because that Z is gonna chow. That's the form I actually wanted in. But this thing here in the denominator looks a bit cray cray. Well, I think maybe we take this and then divide it by 2.78. No, what's 1 over 2.71828? No, it's the same. It's the same. Because just take this. Take this, for example. Okay. Okay. Let me just save this whole expression. I don't know when I'm going to need it. So take this. So you see, my issue is this thing here. I want the coefficient of that guy to be 1. So I'm going to take this. Okay. I'm going to divide. I'm going to divide by this. So I want to pull this out as a factor. So, but how would that work? Let's just see. 1 over for her body. We should end up with Yeah. Yeah, you just divide by that. But yeah, you divide by, no, if you divide by it here, won't it be, no, it's not, eh? It will be tip and tie, huh? Will it? No, okay, it's strange. It's strange, but okay, let's do it. Um, it's strange, but yeah, let's do it. So 0.139519 is 2.718287 minus 1.63127 all over z minus 1, 2.71828 z squared minus 2.89378z plus 1. Okay, pull out 2. So this becomes 0.139519 divided by 2.71828. That equals 0.05132. That's 2.71828Z. Yeah, but you could also pull that out from the top. It's the exact same constant there. To 8, it's the exact same constant there. So you'd have 0.139519. Z to Z minus, what's 1.63127 minus 2.71828, 0.6, which is where we had our other 0, was it not? Roughly, yeah, no, this thing looks like it's exactly the same. Yeah, no, I was thinking I made a mistake here. Minus 1.06456. Yep. Plus 0.367. Yeah, no mistake. No mistake. Okay, Mukela.
Yes,
Yeah. And the zero order holds Z transform there. Well, it's not. No, it's yeah, it's Z minus 1 over Z. So that chars your Z and your Z minus 1, and then you end up with exactly what we had. Yep. Mukela.
sure. So I'll just try and share my screen once again. Hopefully, Is it appearing on your side?
You are sharing something. Yeah, I can see it. I can see it.
Okay. So there's this question here, right? So it's in the well, it's an example actually. So they're saying we're supposed to sketch the root locus, which the first part I do understand how to sketch the root locus and how to determine the value for marginally stable.
Mm-hmm.
But then they then say locate a point on the locus that corresponds to the closed loop damping ratio of 0.5, right?
Mm-hmm.
And then they say what is the value. So like the problem is actually locating this point over here which they're talking about, because when I look here on the example, what happens is like I don't know how like exactly they chose the point, because they just came, okay, they determined the value of the angle using that damping
Mm-hmm.
factor. I do understand.
Uh-huh.
And they had like the values of theta 1, theta 2, theta 3, which is
Mm-hmm.
from when they were determining for the thing for the root locus. Where is it? Which is here. I I think it's from here, because 60 plus minus 60 will just give me
Yeah.
180 using
Yeah.
same. But the problem starts when they just like give me this to say that at this, then we have our thing, we have our value for S, which is that point, which I don't understand how they prove it when they have these values here, which is
Okay.
different from the
So
question.
so your point is now saying, okay, the question is asking you to find the value of K that will correspond to having a damping factor of what is it,
0.5.
0.5.
Yeah,
So yeah, okay. All right. So let's see how we can set up this problem. So we've got our locus, fine. You figure out from that equation your angle needs to be 60 degrees. Okay, so beta, can you just go up to what beta is? Can I just see that? That should
yeah.
be the angle. I can't, I'm still looking at your. Yeah, we're still looking at your, because finding that point. So okay, let's try something. Let's try something. Let's try something. I hope this works. So you see, Mukela, what you're doing is you can see that beta is 60 degrees, right?
Sure.
Okay, so let me just draw this quickly. Yeah, they cheated a bit there, but anyway. So I'll write this out nicely. And yeah, no, that final value needs to tend to thing. I don't know why it's not. It's a lot of work, but okay. So check it out. Okay. So somewhere, ah, yeah, no, I really need to switch this up. Okay. So somewhere you've been told that, okay, the angle you need to make I don't know if that's accurate. It's like what, 60 degrees, right?
Mm-hmm.
And then I don't know what the exact plot of this thing is. How is it coming in? Is it coming in like this? What does it look like? Can you just show me? Okay. So where's your breakaway?
Breakaway
So it's
point.
breaking in. So okay, so that's one. The X's are the poles, or what? Because I see something strange. I see 1, 2, 3.
Yeah, there are 3 poles. There's one at 0, there's one at -2, and there's one at -5.
Okay, cool. -5 we don't care about. Cool. So can I share again?
Sure.
So we have this pole, which I don't care about. The other one you
Just a
said
second.
is okay. No, let me share again. I don't know what's happening. Okay, can you see me now?
Yeah.
Okay. So you got a pole there, and you say you have a pole somewhere here, okay?
Mm-hmm.
So life is going to carry on as normal. Remember, points to the left of the odd critical frequencies lie on the low key. So this is 1, that's 2, that's 3. So this has to be on the low key. So however it's supposed to go, however it's supposed to go. Okay. Now it's drawn quite badly, but let's say for argument's sake, this here is 60 degrees. Okay,
Okay.
fine. So you know that when this thing is 60 degrees, okay, when that thing is 60 degrees, it's going to pass through the loci at some point, right? We're
Sure.
assuming that that point is on the loci. So here's what you do. You say that, okay, and your question is, how did they find said points?
Yeah, the point thing, that S point, do they like choose it randomly? Is there a way to like calculate?
No. Well, the thing is, what you're asking for is, what's this point here? Whoa, pizza. This point here. What's the breakaway point?
Breakaway point should be just check what was this -3. So there are 2 breakaway. Okay, just make sure that what I'm getting is.
Yeah, because what you can do is, how would you do this?
So there are 2 of them. It's -3.79 and -0.884.
-0.884. Okay, because what in essence you are aiming to say is this point here, S, which is equal to, there you go, if I find the angle of this guy, which is going to be arctan omega over alpha, this guy I know is equal to 60 degrees. Okay. Now you know something about where is this point here? Where does it become marginally stable?
It's marginally stable at 11 point. Nope, I'm lying. From the 70.
Here, at this point is 70.
Yep, that's what they're saying. But let me just check on the sketch.
Sure.
No.
That's high.
That point, the intersection point, is actually k is equals to 70. But
Okay, but on the imaginary axis, where is it? I don't know, boss.
Here they're saying that the roof array marginal stability occurs at k is equals to 70. So yes.
Yeah, okay. So then it's got some point there, because now what you need to do is you know something about this. You know that this point there is going to be bigger than 0 point. But I mean, no, man, there is a way to do this. There is a way to do this. Just give me 2 seconds. I do have notes on this, but this is moving more into compensated design as well. But no man, I know for sure, I know there's a way to do this. I know for sure. Let me just show you the notes. This one I found is quite easy. About trying to find out whether or not a particular point lies on the loci. Yeah. PD, find a value. This shit here. So a particular point, yeah. So yeah, they're picking a desired point. So what do you know about that point in relation to where you're starting? It's got to be in relation to where you are starting. So how do we construct that? The desired dominant pole minus zeta omega n 1 minus square root. Okay, try that. Okay, let's try this. What's your omega n?
Just a second. So omega n is the frequency of oscillation at marginal stability, right?
It's just this thing here. So if you look, it's this. How do I say this? So you can get it in many different ways. In fact, let me also open Burns. What example are you looking at?
It's on page 120, 126, from 126, from there the bottom, then it continues to 129.
126, you say?
Yeah.
Okay, I think I've seen. Oh, it's this 60-degree thing. Oh, okay. So 126. Okay, it starts there. Okay, so omega n here. What is this? Okay, so the controller is what? I'm just assuming it's going to be just a straight up K over S. Okay. Or you could just assume it's K. So what is omega n in terms of... Yeah,
Was
okay.
I supposed to like simplify the denote? Okay, it's actually a third order if I do that. So,
Yeah, it's technically a third order, but all of these things when you so if you're saying omega n is... okay, no. With that characteristic equation, what do we know? What do we know? What do we know with this characteristic equation? Because in essence you are picking. You need to figure out, okay, where do I need to pick that position such that I get the desired characteristics. And what is the question asking of you? All it says is what? A zeta of...
it's a thing 0.5.
Yeah.
Just make zeta to be.
So you solve the characteristic equation, s squared plus 2 zeta omega n plus omega n squared, you get s is equal to minus zeta omega n plus omega n plus j omega n square root 1 minus zeta squared. So square root 1 minus... Yeah, I think it's coming along. It's just that I feel you are going to have one other thing that you need to know. Okay, so coming back here, your desired pole minus zeta omega n plus or minus j omega n square root 1 minus zeta squared, okay? That's what you're saying. Now, zeta, you said to me, is 0.5 minus 0.5 omega n plus j root 3 over 2 omega n.
Okay.
Now, what is the natural frequency of that system? So now if we come down here, they just said at minus 0.7. So if I say minus 0.7 over minus 0.5, now just trying to reverse engineer. So according to them, omega n is equal to 1.4. Now, if I put this in here, do I get the right thing? I should. There's no reason I shouldn't. I get 1.21. So now how do they arrive at an omega n value equal to 1.4?
Nice.
Okay, let me just multiply out. So if you take, so here's their combination. So they're saying GS HS is equal to K all over S plus 2, S plus 5. If you take this combination, right? If you take this combination, ignoring the S part for now, 2S plus 7S plus 10, right? And if I say equating coefficients 2 zeta omega n is equal to 7, omega n is equal to 7 over 2 zeta. No. If omega n is 0.5, I mean, if you said zeta 0.5, yeah, you're going nowhere. It's going to tell you that omega n is 7. But no. What other information do we know in this question? There's got to be a way to infer it. There's got to be. Locate a point on the locus that corresponds to a closed loop damping ratio of 0.5. Okay, we know that the closed loop damping ratio at we don't know anything else.
Well, maybe there is an answer in the first part. I just don't see it. I don't know.
Yeah, because I haven't said anything to you about rise time, settling time, anything else that you can infer omega n from.
Yeah.
Have they said anything like that? Because what you have is you've got the angle and you've got zeta. So now between
We just sketching from like what sketching the transfer function using the normal procedures Prof calls it.
so look, so with this, you're basically saying if I arctan will it matter? Will omega n be child here? No, it's no, I don't think. No, it's going to matter. It has to matter. No, I mean, if you look at that ratio and you do it now, you'll get 60. So why is omega n what it is? Because if you pick any, how do I know that that point's on the loci? If I picked omega n, let's say to be 7.
Yeah. The angle will still be the same, but the wow. Okay,
You see, what?
Okay.
Because if you arctan that as it stands, your angle is going to be 60. Your angle is going to be 60. If you put in the omega n that they put in, sure. But like this, if you arctan, if you just say root 3 over 2 omega n over that guy,
Okay,
what you're saying is,
could you please like check maybe page 390, because here it says page 390 is like an appendix and it gives the MATLAB code for determining this thing. Here it says here a line of zeta 0.5 beta 60 degrees is drawn together with 4 omega n circles, which is omega n is equal to 2, omega n is equal to 4, omega n is equal to 8 radians. At the MATLAB prompt, the user is asked to select a point in the graphics window if the intersection of the complex locus with if the intersection of the complex locus with the 0.5 line is selected, the following response is obtained. Then they get their 0.71 and 1.25. So I guess maybe it's trial and error. I don't know.
yeah, but you see, like this to me, this is but given that, okay, if I put in, why is it that point specifically? Because if you're doing it this way and you're just arctanning, that you're gonna get 60 degrees all ends up. If you do this, if you plug in your zeta here, You're going to
Yeah.
get 60 all the time. So
So
why that? So what you must be saying is that that point that you're picking doesn't lie on the loci. So you're saying that you could put in theoretically any point you want there, but then how do you know that it lies on the loci? That's the question that's the question I think now you need to ask yourself with root locus. What happens if you try and put a point that doesn't lie on the loci? What are you gonna get? So you said that's page 120.
no, that's page 390. It's example 5.8. That's like it's a small piece of code for MATLAB.
Yeah, no, I was there, but I mean the original example.
126.
126.
Yeah. So select a point in the correct experiment. I guess. Well, actually, I did see a similar question to this, I think in 2018, so that's why I'm a bit worried about it. But
Yeah, no, we will go through that. I just want to see where now, how you find that a point lies on the loci. I mean, I did know this. There is a way. There's definitely a way. There's definitely a way because even how they get cos beta is equal to just zeta. It's minus zeta omega n. Hence, a point P on the S-plane can be represented in figure 10 as, wait. So go to page 122.
122.
Okay, well, I'll just bring it here. I'll just bring it. I'll
It's
just
fine.
bring it this side. So you see, to have an acceptable transient response, zeta must be greater than 0.5. Straight up. That's what these people are saying, like from the jump, okay? Now they're saying that this point, a point P, is given by minus zeta omega n squared plus omega n squared root 1 minus zeta squared. Okay, so OP is somewhere. We know the zeta, but again,
Could I
simplifying,
get
they said OP
omega?
is equal to omega n.
Could I get omega n simultaneously? Because when I'm looking at that equation 5.52, I know what my beta is at 60. I know what my zeta is, which is 0.5, and they're saying here that the magnitude of zeta and omega divided by omega will give us cos beta, and I think on that page 122. I don't know. Yeah, just find that.
Yeah, but you see here they're saying that OP is equal to omega n. So whatever point we put here is equal to essentially omega n. But okay. Okay, fine. The angle criterion. Yeah, so you see, shows that a vector of, for S1 to lie on the locus, then this, where's phi 1? Where's the point that I've got? So they must all sum up to 180. So for a point, a particular point. No, but I mean, if we maintain that ratio, then yeah, I knew there was that thing, a point lying on the locus, the angle criterion. All angle vectors between the open loop poles and zeros to point S1 must equal 180. So it's 5.58. It's definitely that. So if you pick something that's not that, then you can't be speaking about the same point.
Yeah.
So then this angle here is this angle the same as beta 1? Is it?
I'm not sure which angle you're pointing at.
So I'm scrolling down. Where was that angle criteria? So here, figure 15, 5 point, so it's 5.81. So,
I have to like reshow your screen because it's not updating on my side.
oh, okay. Oh, sorry. I had it open on two places here. So I knew there was some criterion which specified whether or not a point lies on the loci or the loci. It's up here. It's this angle criterion here. Have I gone too far up? I think I have. So OP is equal to omega n, straight up, right? That point there, that's omega n. So now, where is this angle criterion? This thing here. So if that's the point, you're saying you add all those angles up, but you're moving in a what? Anti-clockwise manner, right? If we add all those angles up for the poles and the zeros, so whatever point you have here, that should sum to 180. So in other words, the angle that you require will be all of these guys minus 180. That'll give you the angle of that guy you need. Yeah.
Also,
So you say, yeah.
Also, before we move away from this, how do you select that S1 on the angle of criterion?
This you select usually given desired transient response. So you have certain characteristics. So that you'll get from your settling time, your overshoot, and that usually specifies omega n. Then with that omega n and the damping you want, you then already know the point. Then this is checking, okay, when you find the angle of that point, does it actually lie on the locus? Because if it doesn't lie on the locus, you can't actually attain those specifications. Now here you've got almost like the reverse. You're saying that, okay, the angle, you're saying that this angle here at that point is 60 degrees. Not so. So now, but will it be 60 though? Nah, I think here's where the simultaneous nonsense comes in. So this is what you're going to say. Okay, let me just scroll to the page. What page is that? 124. So look, this is what you're going to say here then. This is what you're going to say. You're going to say, I'm using equation 5.58. So what you're going to say is theta 1 is equal to 180 degrees minus. Oh no, that's just the pole. So from whatever point you want to pick, you are saying, wait. So how are you constructing those angles here from your particular point?
Because that's what I'm asking. Also, in the 2017 test, he also gave them the solution and he selected a point, and to me, it didn't really make sense why I was selecting that point, and was calculating the angle of departure, and from the graph, which can I please share my screen?
Yeah. Okay. Sure. Go for it.
Might not make sense.
Because what I'm trying to find out is,
Sharing anything?
yeah. So no, this angle criterion, you need to see what is actually happening here, because that's the long and short of it.
Is it sharing now?
Yeah, it's sharing. Yeah, it's sharing.
So what he did here was like, okay, he calculated everything, which I do understand. Like I do understand how to get the poles and all of that. Then when he came here, he was like, angles of departure of the complex open loop poles we consider as infinitesimally close to P1, right?
Mm-hmm.
So considering S to be infinitesimally close to P1, he's not really saying what the value of S is, or
Sure.
like, but it's just saying it's close. That I do understand. Then it says it's calculating the angle of departure for it's just the angle of departure. Let me just say so. But when it comes here, the angle of departure is actually negative 63.43, and
Mm.
for P1 actually. Then for P2 for the second pole it's 63.43, which does make sense when I use a completely different method, saying that I'm calculating the angle of departure with reference to the x-axis here, and
Yeah.
I'm in the angle here. But in this case, there's this angle of departure which is way, well, it's more than 180. I don't know why he's saying it's 63.
That then you see that has to be the negative 63 that he's talking about. So the one, phi 2, that's the 60 whatever. Then this one has to be the negative if he's going, but he's going the other way around. So you're right. So it would be
It would,
180 minus 120 something. So I think that's given me the an idea here.
so it's
So
actually 63 in like here. I don't know if you can
yeah.
see my cursor.
Yeah, I can see your cursor.
Okay, because I was thinking that maybe it's supposed to be like negative 63 here, because that's what I determined to be able to like to have negative 63 from this point here, P2, or
Yeah.
let's just say this one is P2 with reference
But
to
but
the the pole, yeah, the pole here, the origin.
yeah, because that this angle that he has there is like 270 something. Is it? No, 90,
No,
180. Yeah, it's more. It's like 100 and 190 whatever. So if you say negative 60 something plus, hey, no man.
exactly.
Okay, I think we can calculate this. I've seen now what's going on with this angle criterion. I've seen now what's happening. So you are picking any arbitrary point there, and you're saying when I sum these angles, so it's all poles minus zeros or what?
That's funny now.
Where is it? I seem to have lost it. So yeah, it's
Yeah,
all your pole angles minus all your zero angles.
yeah, I didn't hear most of what you were saying because my PC was frozen just when I stopped sharing the screen. So,
Yeah, no, what I was saying is no, you can most definitely um uh, see this, but to me looking at this, it's almost like you're going to pick. There's something you need to pick somewhere and then calculate, good sir. Somewhere you're gonna have to choose your poison here. So for example, what you looking at. What you're looking at is this line here. Okay? So somewhere you're gonna have to pick. So we've got whatever, it's exaggerated, but fine. Now you're saying that there is the point. Okay, let me draw it a little bit further up. That here is your point S1. So I was saying the only point of reference that you have is that you know that the real part of that must be greater than whatever it is, 0.6 something, and the imaginary part of that must be smaller than wherever it crosses the imaginary axis, that intercept. Now you have a pole here. You have a pole here. And what? Where's the other pole? Other pole must be somewhere here.
I think it's let me just check.
Because I don't see any zeros here.
Yeah, it's there. It's there. There's no zero yet.
Yeah. So now, what you're saying, good sir, is this. This and that. So this angle that way. This angle this way. This angle this way. And now you're saying when I sum all of these up, I need to get 180 degrees. Okay, so looking at it, this is the acute one. This is going to be small. This is the one which is going to have to be the biggest. And then you have something in between here.
Sure.
All right, so now, gosh, because what I'm thinking is you can pick points, right? Provided you keep the zeta omega n thing the same. But yeah, and like I don't. How are you gonna know you're gonna violate that zeta? How if that angle here is greater than 60? Because you've got some other constraints which I think is also breaking here. That thing here, that guy here being 60 degrees.
But what exactly does the 60? Where exactly is the 60 degrees, if I may ask?
So the 60 degrees, good sir, it's specifying lines on the actual. It's specifying the lines on the actual loci. So I'll show you. I think here. Here, I think they draw it and they explain it. They explain it nicely. So you see here now. Here now is you see some desired point, right? So whatever desired point, this is basically just showing you pictorially what we know to be true graphically. So omega n multiplied by 1 over minus square root of zeta squared is there. And then the real part is just zeta omega n. Now, this 60 here is from the actual origin. So for example, if I start here at the actual origin, it's these lines which stretch out like this and like this. So where that thing has the angle that thing makes with yeah, but it depends. I mean, if you yeah, but the thing is you're only going one way. So what it's basically saying is so if you think about it like this, you've got this, right? You've got 60. Your root locus is going this way.
Sure.
Right? No matter what value of omega you keep increasing, that angle will always remain 60 provided you've got the same ratio. In other words, are you sitting on this line? If you're sitting on this line, the angle is always going to be 60. You see? That's why for whatever omega n value you put in, provided you have minus 0.5 and root 3 over 2, the angle is always going to be 60 because you're on that line. However, you can see that not all points on this line here will lie on the locus. So that means the bigger ones we know are out, and we know that our actual real part, so this guy here is getting more and more and more. Is it positive? Yes. This guy, because this is the left-hand side, right? So on this root locus, this guy is getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. So we've really only got this point to aim at. The first time, the first point at which that thing is 60.
But how would we know that that is the point which is lying on the root locus?
So now you now have to kind of, how do we put it, like
you think you could bring us this question though?
Look, I don't know. Like I'm worried, and your contemporaries seem to be okay with it. Very, very nonchalant. That's why I said, listen, I can't just give you answers without giving you a story time, because Prof. Van Veek does repeat questions. But if he decides this year I'm not, you're gonna be screwed.
Yeah,
so
software, I don't believe that anyone will repeat the question.
Yeah. So you see how you know that point. That's a very, you're trying to solve an equation here. How do you set this up? Because what in essence you are asking is, okay, you have some, would this be a radius? Would this be like an intersection of two circles? I think with your thing got me thinking. So you've got a radius, or like a ray here, right? But then how would you know, where would that S is equal to R theta? This is like, what would you call, what do they call those things in mechanics? Like a sector or a something. This slice. And then you say that this guy is going to be equal to your entire root locus. And then where this is equal to this is where that intercept is going to be. So this here, what is the equation of this line? What is the equation of that line?
The line which intersects the root locus.
Yeah, this zeta line here. What is the equation of this?
The gradient should be.
This is this not this SD thing? No, this is no, but no, this is lying on a line. So okay, no.
But bangz, how would we get the thing, the radius of the root locus? Isn't it that the radius is infinity? Unless if I don't understand.
No. You are right. I'm just trying to think about this in terms of circles, because remember you spoke about the circle there. So what I would say is, how I'd approach it is like this, good sir. So look, this thing that we derived, where was it? Here. Is this not a line? Is this not a line? If we plot this, is this not going to give you a line? Not so.
It should give you a line with a gradient. Okay.
Yeah. So if you yes.
Whatever the line is complex, I don't know.
Just think about it in terms of, these are your y points, like on this plane here. If you make omega n, okay, because you've got two, so you can see there's you got some conjugate action going on. So if you make omega n increasingly more negative, you'd be going either up on the one, or you'd be going down on the other one. But this is a line. So what I'm thinking is, you say this guy must equal, where's your entire root locus equation? Where's the entire root locus equation?
I'm I'm not quite sure I understand what you mean.
I'll show you now. I'll show you now. The thing that we used to set up, the whole k multiplied by something, the plant. It was k over. I saw it now. It was like over s plus 2 something.
S plus 2, S plus 5.
Okay. So that's what sets up the arc.
Can you
That's what
please?
sets up.
Okay.
Uh,
Okay. I can. It's now. It's fine. It's fine.
okay.
So
So
maybe.
do you know what value of k you need to be at the breakaway point?
No, they actually determine the k value. Oh, the breakaway point.
Yeah. What value of k do you need to get to that breakaway point?
Okay, let me just remember this. So the k value at the breakaway point is when it starts diverging to infinity, right? When it starts pointing out into other different directions. But is that where it's marginally stable? Am I right?
No, that's where it intercepts the y-axis. The breakaway point, when you take this guy, you differentiate, you equate it equal to 0. Then it tells you at what point it leaves the x-axis. So in other words, this point here, there. What is that point there?
Okay. So we differentiate, then
Equate equal to, yeah. So just like the procedure that we had here. So yeah, so you say 1 plus this guy equals 0. So you differentiate this and it's equal to minus 1 over that thing, basically equal to 0. So then you figure out what's the breakaway point. When you solve for that, it should be less than this minus 0.7. Because what I'm saying is the point that you're going to use there, I'm going to say make that point infinitesimally on the real axis bigger. So at least you now fix yourself somewhere on the real axis. And now you say, okay, given that point, what does the other one need to be such that I get this angle of 60? That's what I'm thinking.
Yeah. That makes sense.
Because the other way would be you saying this thing here, that you want to say this thing equals your entire root locus. And then what you'd say is, now that I've done that, when does this thing actually... Ooh, but how do you explicitly find the angle of points? Yeah, you'd have to say, when is this equal to that? So I think what you'd have to do is you'd have to say, yeah, I don't know, this is just a waffle, but the equation of that line, you then have to substitute in S is equal to J omega here. But then you still have that K to contend with. So that's going to actually get you. No, but the K just shows you how it moves along. So I think you can minus the K. You say S is equal to J omega and you equate it to this thing. I don't know. It's just a hash. Let's see. Let's see how this.
When I differentiate, I get a second order, and with the second order, I now get like two poles, which is like negative 3.9379 and 0.84. Well, negative 0.84, which is
underdamped.
No, I'm just differentiating the denominator of the equation.
Yeah, so those are your breakaway points, not so then.
Yeah.
So yeah, you see there's one which doesn't make sense, as you saw with Duncan earlier. There's one which doesn't make sense, which you then have to reason out with your understanding of the root locus to say that, okay, how would this thing move? Where would these things actually go? So okay, I think I might have one last idea, but yeah, if it's not this, hey, Mukela, we need to call it a day. Some of us have work here. Now you put me into this thing. So 1 over j omega minus omega squared plus 10 plus 7 j omega is equal to, here's what I'm thinking you would say. If this doesn't work, I hope it does. This is the only kind of rationale that I can come up with. Plus j root 3 over 2 omega. So here's what I'm thinking we say, Mukela, here. So I plugged in j omega into the root locus formula. So I've said j omega is equal to minus omega squared plus 10 plus 7 j omega. Okay?
Sure.
And this must be equal to minus 0.5. I know it's omega n, but I could call this either omega n or, so I'm just going to call this omega plus or minus j root 3 over 2 omega. Because it just occurred to me that k just is you showing how for various different values of a gain, these poles move. Okay? But this
Sure.
locus exists. This actually does exist. It's just when you have different values of k, it shows it moving. So now my plan is to say, okay, this thing, when is this thing going to equal that guy there? Because points must exist. There must be a point where this thing actually, the equation of that line and the equation of this locus, they intercept. There's got to be a point. So now I'm going to put this in Notepad and then see, does this actually occur? Yeah, it's a long shot, but I think mathematically, at least, I think it's sound. I was actually speaking to my friend who's actually a PhD graduate in control, and some of that Kalman digital derivation,
Yeah.
you only find it in that book Raven. Only find it in that book Raven. Is equal to minus 0.5. I just hope it can solve it without timing out.
Yes.
So root 3 over 2 that's equal to 0.866025403. So let's see if Wolfram can solve it. Otherwise,
Minus 0.5 x. Yeah.
what is it saying to me?
I think you're supposed to use. Okay, use the I. I don't know. I think you use J somewhere instead of I.
Oh yeah, I used J there.
Yeah.
Yeah. Because I was thinking, why are we getting two guys coming out here? Eh? No, man. It should be this whole thing. It should be this whole thing. The denominator, yeah. This whole thing.
Yeah, I'm not getting it.
So okay, this is what we are getting. Now, riddle me this. Where was that breakaway point?
The breakaway point was at -3, -3,
Negative 3 point what?
-9, just -3.79 and -0.88.
Negative 3.79 on the real.
Yes.
Yeah, shit, this is not coming out because what you should be getting. Let me try the minus here. Who knows? Let me try the minus because you should get a point at least that has a real value. That's to the right.
Omega n. Yeah, I guess I'll just I don't know. Oh, there's always room for growth, you know.
Yeah.
Uh,
Give me this. So if I put in 3 points, if I put in 0.518306 and 3.14091, the angle should still be 60, right? No, that angle is definitely not 60. No way. Positive 180, man. Nah, no, it's not. Yeah, was worth a shot, but
well, I can always use like MathLab if it comes out. I mean, I do have that piece of code on the appendix, so yeah.
yeah, I mean, like, for sure. For sure, I think that code we're actually also going to use. But how you gonna explain you did it? That's going to be tricky because I think the issue here is, yeah. Yeah, that's close. Yeah,
It's fun.
yeah. No, I think my problem is you actually have to substitute in. No, it's wild. It's wild. It's wild. I don't know if I did. Did I put this in correctly?
No, I usually
I
put
didn't
it with
put this.
the same answer.
Hey! I didn't put in correctly, you Mugel. I did not put this thing in correctly. Hey, man.
We got the same answers, I think.
Hey, man. I did not put this thing in correctly. I forgot a 7 there.
That would make a difference.
Yeah, it should. It definitely should make a difference. Can you see these?
Eh.
This is what? Minus. Let's try plus. Let's try plus. Where was your point? Minus 3 points?
3.88 and negative 3.79.
Yeah. Yeah, no, it's still showing itself. Yeah, it's still showing itself. Because I think that's the closest one that I would think of. But I think even there, the angle is not what it needs to be.
But isn't it that's actually omega n, and omega n is supposed to be a real valued thing? Oh, I mean at all level, obviously.
Yeah, omega n should be a real number. So you want to take magnitude?
Actually, let me try that.
Yeah,
Okay.
take magnitude of some of these things. Take magnitude. Let's see.
And but
Because there's something here which is chilling on the real axis. I can't see it too nicely, but there's something there.
okay, that's not correct. 0.11 0.418. Nope. 0. No. Uh, looking for 0.45.
Because this is the closest thing I can think of to say, because otherwise I don't know how you're gonna. So what I'm seeing here is like 2.3.
So for that last one, the omega n becomes 1.53, which is approximately similar to 1.4.
But I tell you
So,
what, I didn't put square root 3/2 here. I used an approximation. Square root 3/2. Yeah, but also how you're supposed to discern that. That's a chat for another day. But
yeah, no, it's fine. I just
put this one in. What do you get?
160. It's actually the same. It should be
This
the
one
same.
still the same.
It's actually the same answer.
1.5. Yeah, but I mean, there it is. There it is, good sir. It has come out mathematically. It has come out. Although you have to do a little bit of fudging, but because even their answer, let me be honest with how it is, I don't get that angle exactly. I don't get that angle of 60 exactly. So if you put in what are we saying? 1.53474.
Yeah, I get 60.7.
But hang on, could you not pick your real part somewhat, and then I don't know, thumb suck an imaginary value and then get your angle?
How do you know that it's on the thing on the root locus?
Because the real part you make that, yeah, still, yeah. How do you know? Yeah, you don't know. So yeah, I just want to see this one last thing. So if you plug in the 1.5 minus 0.5, what is it? 1.5347. So you get, nah, Mukela, this is the thing, dog. This is the thing. Because what you'd have to do then is, now you have all those points, so now you'd have to find magnitude, plug those in, and then use the angle criterion. But nah, this is the thing. This is the thing. Like mathematically, it works out. Okay, excuse the fact that we have to find magnitudes, but and then if I find the angle of this, if I say arctan 1.34 and 0.767, yeah, I get 60.2. And their value, yeah, so using an omega n of 1.53474.
Okay.
Now I wonder, will you get the same value if you use something else? Unconscionably, no. Unconscionably, no. Surely. Because if you put this thing as 5,
Yeah.
well, I mean, look, you still will get
The same, but the position on where is it? It's no longer on the.
it's no longer on the. It might no longer be on the locus, yeah. So what you need to do is, nah, but Mukela, this thing we can do it, man. This thing you can do it. The thing is, all you're saying is, listen, the value that you put in, the key thing here is that breakaway point. Once you know where that breakaway point is, you can then say, okay, let me try and mac a bit. You know, once you know where this guy is, the value of any of those things that you put, the value of any of those guys that you put need to be somewhere close to this guy. It needs to be somewhere close to that point there. The real part anyway. The real part anyway. That rationale, I think you can explain your way out of. Because if you go and have a real part which is far away from that breakaway point, No. And then I think needs to be bigger. The breakaway point is what?
Negative 0.899, and there's also negative 3.79.
Yeah, so somewhere there, but you don't care. So your inequality is that omega. So this omega n value needs to be such that when you multiply it here, that real part is greater than 0, but less than this. So you got an inequality. You got an inequality to at least mark with.
Okay. Okay.
You do. You
Yeah,
do.
I'll just have another look at it, and if it still takes time, I'll just leave it. Honestly, I mean, there's no need to.
Yeah, man. No, but nah, dog. You can try some things. What was that breakaway point you said?
0.899 884. Sorry. Then
Negative
there's
zero
also
point
884.
884.
Yeah.
Yeah, okay. No, we're definitely moving there. And then
So you want to use the turn sign to be able to determine the
yeah, because I'm thinking you could even split this up into maybe a small triangle here to say that okay, that's the point I'm using as my base. Then I'm going up to some point here.
that would work nice for that example you used where we are like where you were demonstrating how they break away. Well, I think it was the other or second part, I don't remember. That would make better sense, but with a curve, then yeah. Well, you can always say that k is finitely larger than whatever value you want to get there. Oh, which does make sense because we have that value as 1.25 and k is 70, so you could always say that you're assuming
Yeah.
that marginally stable very far away, so the value which you're going to get will actually be some type of a triangle, and yeah.
Yeah, no, I'm moving that triangle there. So then what you need, this value here would be, yeah. So look, you could just say that you're gonna stop somewhere shy there, and then you're gonna go up. Because if
Yeah.
you see here, if you zoom in here, gosh. Yeah, no, that can work. That can actually work. If you say you want to stop somewhere there with your triangle, and then you know it's going up. And then where's the 60 degrees? 60 degrees is in here. 60 degrees is in here. You pick some point there. And then now,
Well, you could
how do
choose
you?
the away point and use turn, or is it turn? Yeah, use turn to determine the imaginary value.
Yeah, actually. But the thing is, why I'd be a bit hesitant to use the breakaway point is because you would be kind of saying that it goes up infinitesimally quickly to that value. So that's why I said you pick something that is a bit further, but not too far. So you see your breakaway point was minus 0.884.
Yeah.
So I'd pick something like minus 0.7 or something. And then you now go here, you then use the tan thing, figure out your imaginary point. Now with that point, you go and use the angle criterion. And then the angle criterion, you'll be able to see, okay, am I far? Do those things sum to 180 or are they not? But you should be close. You should be close.
What you can do here.
Because looking at this, Mukele, if you think about it, every single X point here lies on the loci. If you're between here and here, all of these guys are valid. All of these guys are valid. From here to here, all of them are valid. Doesn't matter what you pick. I'm just saying, don't pick that one. Give me something here.
Yeah, when I use 0.7, I get like 1.221, which is close to what we had, but yeah.
You see. So that's the method then, Doc. That's the method. You come and see how you can make there. You're gonna use good old Pythagoras, or if you try and do some gorilla style things here and then get magnitudes, because this essentially, yeah, it should, but I think you're assuming something about K here. What's the K at your breakaway point? Humor me?
Yes. They even mention it here.
Now you can calculate it. You can calculate it. Once you have your breakaway points, you can then go and shove it into the root locus, and then you can work back. I did it for your lab, and then you can calculate what value of K do you have.
Yeah, I actually
because
ran away from the question, but
because remember, when before you get your breakaway points, you solve this thing here. You solve K is equal to -1 over G of S. Now that point here that you put in here is your breakaway point. So if you say K is equal to -1 over, you can actually work it out. You just plug in the exact value of your breakaway point, and you said to me that S was equal to -0.8. Yeah, no, actually we'll work it out right now. Let me just copy this. That's copied. Fine. So you say this is equal to -1 over 1 over, what was the breakaway value?
-0.884.
-0.884. Okay. What came next? It was -0.884 plus 2, all multiplied by -0.884 plus 2. So the K value is like what? Is it really that? That seems a bit sus, I won't lie.
So you're substituting.
I messed up. What I'm doing is I'm putting in the point at which you have your breakaway, right?
Where are you putting it? In like the
plant.
G of F.
Yeah. That G of S thing here. So this basically, did we even write it down?
So it's K S plus.
Yeah, K over S
Okay.
plus 2, S plus 5.
So you're saying it equals to what?
Huh? So you substitute in the value at which you have the breakaway point. Then you say -1 over that value. That's how you figure out the gain at any value. Any value of your root locus, analytically anyway. That's how you figure out the gain. So now you can see that's beta. That's 1.109. So now this thing that I copied here, I'm going to modify this gain to be 1.109. It's actually bigger than 1.109, but it should help you improve your accuracy. It should improve that accuracy somewhat.
So it's the magnitude of 0.477 squared. Still the same.
Yeah, it's relatively still the same.
Yeah.
But
Hey,
yeah,
thanks, good sir.
yeah, I think let's call it.
Yeah,
Is Mount still around or he booked?
I think it's still here.
You have a question for me? Let me see if this whiteboard actually works. Ah, I need to install this whiteboard. Maybe